Hello, this is Physics Lab 5, where I experimented with the Slinky Drop. So to introduce this lab a little bit, my main purpose was to examine the motion of a dropped slinky where the bottom appears to be held motionless until the slinky fully compresses, and then to create a model to replicate this weird phenomenon. And so the models I used were a tracker motion capture data for the actual video, and then glow script code to make a model for the slinky. The fundamental principles used were spring force, force of gravity, and Newton's second law, and the main result was that I succeeded at replicating the motion within a coded model. So first, to explain the physics concept used, we need to derive the position and velocity update formula from Newton's second law, which we can see here from F net equals delta momentum over delta time. That would be divided by mass on both sides, and we can rearrange to get our velocity update, and then from that we can find our position update. Also, we have to be aware of our forces present, which in this case is force of gravity and the spring force, and the equations for those are on the left. And as we see, the gravity force will be constant, but our spring force will change based on the length of our spring, which will be important. So within our actual experiment, you can see the video on the right, but our main conditions were that the system was modeled as mass on two ends of a spring, and this total mass was 0.22 kilograms or 0.11 on both sides. And then we found that our initial stretched length of a sprinky fully compressed is just 0.064 meters. And then experimentally, I found that the spring constant would be 3.3 newtons per meter. And so with this, we assumed that there was no motion towards or away from the camera in the video, and it was just straight up and down. And then we also had to assume that the mass for the slinky was on the two ends and not distributed throughout with the center of mass like it probably really is. And so this motion was also tracked right after we released this slinky, so then we would not have to account for the initial velocity. And as you saw in the video, it seems that the bottom does not move at all while the top catches up to it. So to put this model into code, I first had to make vectors for the velocity and position of both the top and the bottom of the slinky. And then within a big while loop, which is under 0.25 seconds, the length of our slinky drop, I had to update the velocity, position, and force on both the top and bottom of the slinky, which is also changed by the length of the spring, which I also had to update. And I updated that using the difference between the top and the bottom of the spring after each loop. And every time this loop resets, it is updated by 0.001 seconds, which was the time between each frame of the video experiment. So for our actual code output, if you look at the top right, you can see that the coded model resembles the video of the actual experiment greatly. And you can see that the top position of the slinky does go down over time to match the bottom, whereas the bottom fluctuates a bit, but if you look at the final and initial positions, it basically sticks right around 0.8 meters below the top. So looking at the comparison between our coded data and our experimental data, first looking at the bottom chart, we can see that the bottom with the code fluctuates a bit more, while the experimental results just kind of slowly drifted down. But if we look at the final and initial states for both of them, we can see by looking at the axis on the side that they barely moved, only about like 0.015 meters or so. Whereas at the top, we can see that the top portion of the slinky moves down greatly to reach the bottom of the slinky, and our results from the experiment and the code for this one are basically the same. So to finish out, we can ask, why does this phenomenon occur? And I found that it was due to the spring force of the slinky on the bottom pulling up, equalizing with the gravity of that portion of the slinky pulling down. So it seems to be held motionless as the top of the slinky pulling it up and the bottom gravity pulling it down equalizes. Whereas the top, its spring force is down as well as gravity, so it naturally comes down to match up with the other portion of the slinky. And so why does our coded model deviate in this bottom portion? Instead of slowly drifting down, it kind of goes back up a little and back down. And the reason for that is because our center of mass in the slinky in the experiment is changing greatly as the coils of the slinky slowly go down. But within our code, I was only able to do it with a point mass at the top and the bottom. So it seems to be pulled up a little bit and then come back down instead of just slowly drifting down.